depending on the situation. So what I'll do in this lecture is just review 3 coordinate systems for you and their line elements and surface elements and volume elements so that you can use them easily. I'm going to review for you Cartesian coordinate system, I'm going to use for you, review for you the cylindrical coordinate system, and finally spherical coordinate system. These are the ones that we use most often in many problems. So let's start with Cartesian coordinate system, in which from the origin a point is given by its x, y and z coordinates. So if I am giving a point x, y and z, I am moving in x direction by x, y direction by y, and then in z direction by z. So this distance will be y, this distance will be x, and this height will be z. Line element in this coordinate system is when I go from point x, y, z to a next point nearby, which could be x plus dx, y plus dy, and z plus dz. So line element dl vector is given as dx unit vector in x direction plus dy unit vector in y direction plus dz unit vector in z direction. Next, I am going to deal with surface area element, and I want you to get used to the idea of surface area having a vector nature. Particularly when we saw that we were calculating flux of electric field, then we used surface area as a vector quantity. Similarly, when we were calculating divergence and things like those, and when we used divergence theorem, we took surface area as a vector quantity. So in Cartesian coordinates, I want to identify surface area, perpendicular surface area in x direction, surface area in y direction, and surface area in z direction. Surface area in x direction by convention is going to be perpendicular to the x axis. So it's parallel to the yz plane, and this distance being dy, this distance being dz, I am going to write surface area element ds as dx, dy, no, it's not dx, it's perpendicular to x, so therefore I should write it as dy dz in the x direction. Similarly, the area element in the y direction is going to be perpendicular to the y axis, and is going to have the x element, x width dx, height dz, and therefore in that direction ds is going to be dx dz in the y direction, and in the z direction similarly I can have this as dx dy in the z direction. So I have defined surface area element in the Cartesian coordinates. Third, I am going to define for you the volume element. Naturally, volume element is in Cartesian coordinates going to be a box, a small box of the size, this is x, y, z, of the size dx, dz, and in this direction dy. So volume element is going to be dx, dy, dz. Unit vectors we already know are x, y, and z, and these are fixed in space. These are fixed unit vectors. They do not change direction, and magnitude obviously is 1. Next, let us consider cylindrical coordinate system, and this is useful when we are dealing with situations where there is cylindrical symmetry. That means there is symmetry about the z axis. Nothing changes with respect to when you go around the z axis. So let me make a coordinate system first. This is my original x, y, and z coordinate system. In cylindrical coordinates, I specify a point by measuring its distance in the xy plane from the origin, and we are going to call this S. I am using the notation used in the book by Griffiths. Then we measure the angle from the x axis, which I am going to call phi, and then height from the xy plane or the z coordinate, which I am going to call z. So this is specified by rho, not rho, I said S, phi, and z. I need 3 coordinates to specify the system, and we have given this name S, phi, and z. You can immediately see the relationship that S is going to be square root of relationship between this and the Cartesian coordinates, x square plus y square. Tangent phi is going to be y over x, and z is z. By inverting these equations, I can also write x as equal to S cosine of phi, and y is sine S sine of phi. Let us look at the unit vectors. If I look at the unit vectors in cylindrical coordinates, this angle is phi, this distance is S, and this height is Z. The unit vector in S direction is going to be in the direction pointing away from the origin. Naturally, you see, if I go to a different point, which is say here, you are going to see that S unit vector has changed direction. So there is S unit vector pointing away from the origin, and it is not fixed in a space. It depends on what point you are at. Then I define unit vector phi, which is perpendicular to S unit vector in the xy plane. So phi is this red unit vector that I'm showing, and this is also not fixed in space. And third is the z unit vector, which is like Cartesian coordinate system, is fixed in space. From the diagram, you can also see that S unit vector is nothing but cosine of phi S unit vector plus sine of phi y unit vector. Phi unit vector is minus sine of phi x unit vector plus cosine of phi y unit vector, and z is obviously z. If I want to show the vector from vector position of this point, the vector position of point S, phi, and z, this is going to be sum of the vector in S direction here plus z. So the vector R is given as S in S direction plus z in z direction. That is the position of the point, the vector from origin to the point. Let us look at the line elements, area elements, and volume elements in cylindrical coordinates. So if I am going from point S, phi, and z to another point, which is S plus ds, phi plus d phi, and z plus dz. Then the line element dl, let us look at geometrically how it looks. So I am at a point here which is s, phi and z, and its position is given by vector r, which is s, s plus z, z. Next point is at some nearby, which is at s phi plus d phi, z plus dz. So r plus dr is obtained, or which I can write as dl is obtained by going from s to increasing distance by ds s plus s. Oh, I'm sorry, I can write it right here. As I said earlier, s is not fixed, so I am also changing the direction of s, plus z plus dz, which is fixed. So by keeping only the first order, I can write this as s s plus s ds unit vector, this is change in the unit vector, plus ds, that is change in the distance in the direction of s, plus z in the unit vector z direction, plus dz z. And this is equal to, on the left hand side, r, which is s unit vector s plus z dz plus dl. Let's cancel certain terms. S cancels. Oh, sorry, this was z plus dl. This term cancels with z on the right hand side, and therefore I get dl is equal to s ds plus ds s plus dz z. Notice if I am moving in s direction by ds, I obviously collect a vector dss. I am moving in z direction with dz, I collect a vector dz, z unit vector. This is the additional term, and let us see what is ds. ds unit vector has changed. So let me look at the xy plane. This was my x, this was my y, and what we have done is ds was like this, it has changed slightly. This was pointing in the direction phi, and now it is pointing in phi plus d phi direction. And the change I will show by blue is this unit vector. This vector, not unit vector, this vector. Notice first that this change is in the direction phi, and this magnitude is going to be d phi times this length, which is 1. So this is going to be s ds, or ds vector is going to be, magnitude is 1 times d phi in the direction phi, and therefore I can write the line element dl as s ds, which is equal to s d phi in the phi direction plus ds s plus dz z. That is a line element in cylindrical coordinates. It makes perfect sense, because if you look at term by term, this is the distance moved in phi direction, this is the distance moved in s direction, this is the distance moved in z direction. Next, let's look at the area element. If I look at the area element in cylindrical coordinates, I am looking at x, y, z, at area perpendicular to s, area perpendicular to phi, and area perpendicular to z. This is the s unit vector. If I am looking at area perpendicular to s, you can see one element is going to be in the xy plane like this, and the second element of this area is going to be in the z direction. this distance is going to be, as we just saw, s d phi, and the height is dz. So, the area element ds in phi direction is going to be s dz d phi. You can see this as units of distance square. Now next, how about in direction phi? I am going to take an element which is in the z direction and perpendicular to the phi direction. This is going to be the area in the direction phi. This distance perpendicular to phi is going to be ds, and the height is dz. And therefore, in the direction phi, ds is going to be ds dz in the direction phi. I should have written direction s here. And if I am looking at area element perpendicular to z, it is going to be ds, and I will be moving like this, ds and s d phi. So, ds, the area element in the z direction, is going to be ds times s times d phi. Sorry, it's in the z direction. You can confirm this quickly. If I were to look at the area of a unit circle in the xy plane, this is a unit circle, that means the radius is 1, or you can also take the radius to be r, then the area would be integration s ds d phi, s varying from 0 to r, d phi varying from 0 to 2 pi, and you get 2 pi times s square by 2, 0 to r, which gives you pi r square. Or if I were looking area of this side of a cylinder, surface area of that, you can see that this area is in the direction s, and if I were to calculate the magnitude and look at this, then the area would be integration s, which for this surface is fixed, radius r, dz d phi, which is nothing but r, dz is going to be the height of the cylinder times 2 pi, which is 2 pi rh, a familiar result. Third, let us look at the volume element in the cylindrical coordinates. I can look at it in many different ways. A volume element is nothing but some area times the height. So I can choose any area I like. Suppose I take the area in the z direction. This area we just saw is nothing but ds times s d phi. So s ds d phi, and height for this volume element is going to be dz. So I can just multiply by dz. That is the volume element. You can make other areas and find that this is